So we're back, and there's just 2 lectures left. The last 2 lectures are on integration by substitution. The idea is that there are some integrals that do not look like any of our types. So now remember, we have a lot of different types out there. I think I counted up 13 different types. And so some integrals are easy to recognize how to do because they look like one of our types. So if I do like the integral of 2x dx, it's just a power of x, so we know that this is going to be basically x squared plus c. Or if you have the integral of, let's say, a 1 over x dx, this is one of our 4 types. That's ln equal to ln of absolute value of x plus c. But some integrals, like the one I've highlighted here, does not line up or match up with any of our types. And you can kind of go through them. It's not a power function. It's not an exponential. It's not a 1 over x. It's not a trigonometric function. It's not a constant. It's not an inverse. The integral is not going to give me an inverse trigonometric function. And so what do we do here? And so the idea is that we're going to use what's called integration by substitution. So this is a technique of integration. And what is integration by substitution? All right, so integration by substitution, the trick is to let u be the thing on the inside or look for a function in its derivative. So we're going to start with this thing, this idea, do you see something on the inside? And so hopefully when you look at this function, and I say, do you see something on the inside? You say, yeah, x squared minus 1 is on the inside. And if you think about x squared minus 1, you'll see that the derivative of that is 2x. And so that's going to help us solve this integral. And then tomorrow, in the next lecture, we'll talk about using the fundamental theorem of calculus along with integration of substitutions. But we'll save that for part 2. So let's take a look at an example to see how this works. And so we're going to start with the example I just showed you right here. And let me copy it down again. And you're going to say, okay, so part A, the integral of 2x x squared minus 1 to the 10th dx. And you're going to look for the thing on the inside. And so if you look here, the thing on the inside is right here. So this is my inside piece. And so I'm going to let u equal this x squared minus 1. And this is called a u substitution. So we'll let u equal that. And then du, which is the derivative of u, and we'll take this derivative with respect to x, so the 2 will come down, and you get 2x minus 0. And instead of writing dx down here, we'll write dx over here. So du, the derivative of u, is equal to 2x, and then we'll write the dx over there. Okay, so once we've made our u and we found our du, the idea is to substitute back in. That's why this is called integration by substitution. The way you substitute back in, let me use a different color. So let's use green here. So here's my u. All right, so here's my u. And so I'm going to let that be u. And then 2x dx, this 2x dx is going to be plugged in right here for this 2x dx. And so this is going to equal, what is it going to equal? It's going to equal the integral. And so this rectangle is u, so I have u to the 10th. So u to the 10th. And then 2x dx is just du, so I'll replace that with du. And now I can integrate this because this is a power function, u to the 10th. And I know for a power function you add 1, so u to the 11 divided by 11 plus c. And then this is equal to, what is e equal to? What is u equal to? It's equal to x squared minus 1. And so this is x squared minus 1 to the 11th divided by 11 plus c. And that's my answer. So let's take a look at what we just did here. And so what we did, right, this big common theme in solving problems, we have a problem that seems very complicated at first. And the way that we solve a very complicated problem is we try to reduce it, do something to it, to turn it into a simple problem. So what we do is we make this u substitution. We look for the thing on the inside, which happens to be the x squared minus 1. We take the derivative of both sides with respect to x, so we get du equals 2x dx. Notice you could write this as, let me get rid of that. You could write this as du divided by dx, so du dx is just equal to 2x. And what we're doing is we're just moving that dx to the other side, so we're multiplying by it on both sides. That way we can make this nice, easy substitution. It looks just like it. But we make the substitution, and then you get a power function. So you reduce it down to integrating power function, which we know, the integral of really anything to the n, d anything, is you just take the anything, and you add 1 to it, and you divide by it, and add c. Right, so integral of anything to the n, d anything, is equal to anything to the n plus 1 divided by n plus 1 plus c. And so that's how this works. Now you can check your answer by taking the derivative. It's a little hard to see because you're going to have to use a chain rule, but the 11 comes down, cancels 11 on the bottom, that becomes a 10, times the derivative of the inside, which is a 2x, plus 0, and you get it back what you want. And so let's look at all of these so you can kind of see, where the inside is. So here, this was the inside. On this bottom one, hopefully you see that that x cubed is the inside. And now this one's a little bit hard to see because the way that we write this square, if I rewrite this, maybe it'll be a bit easier for you to see. If you can rewrite this as the integral of cosine of x all times sine of x quantity squared. This is the same thing, just writing it in different notation. And then it becomes real obvious. The thing on the inside is going to be this sine x. All right, so let's finish this up. Let's practice doing the substitution, letting u be the thing on the inside. And so part B, I have the integral of 3x squared e to the x cubed dx. And again, it's not one of my types, and so I'm going to have to do a u substitution. So I let u be equal to, and it's going to be equal to x cubed. And then when you take the derivative, du, it's going to equal 3x squared. The derivative of x cubed is 3x squared. And then, of course, a dx. And you look at this, and again, let's do this in green. So this is my u. So I go over here and say, okay, this is going to be u. And then this is my du, 3x squared dx. And so right here, this thing I'm going to replace with du. It's really sort of like a cut and paste. So you cut this out and paste in the u. So this is going to equal the integral of e to the u. And then I cut out this 3x squared dx and I paste in the du. I substitute in du. And now this is the integral of e to the u. And I know that the integral of e to the anything, d anything, I ran out of space over here, but it's equal to e to the anything plus c. So it doesn't matter if it's x, it doesn't matter if it's y, it doesn't matter if it's mom or dad, whatever's here, same thing here, it's going to be e to the whatever's there plus c. And so this is just equal to e to the u plus c. And then don't forget to substitute back in for x stuff because you made up u. And so this is e to the x cubed plus c. Again, you can check your answer by taking the derivative of this. It's a chain rule, so you get derivative outside, which is e to the x cubed, times the derivative of the inside, which is 3x squared, plus 0. And it checks. All right, so that one checked, and that one checked. And then finally, let's do part C. So on part C, I have the integral of cosine of x. And then let's write it like this so it's real clear. So sine of x, quantity squared, dx. And then I'm going to let my u be the thing on the inside, so that's going to be sine of x. And then du is going to equal the derivative of sine of x, which is cosine of x. And then I have dx over here. And you just match these things up. So u is always easy to figure out. So here's my u. It's sine of x. So wherever I see a sine of x, I replace it with a u. And then this cosine of x dx, this is my du. So I can replace cosine of x dx with du. So let's do that. And when you do it, this is going to be the integral. I have u squared. And then cosine dx is my du. I realize I just need to integrate a power function. So I add 1 to it, divide by it, plus c. And then make sure you plug back in for u, get everything in terms of x. So then I'm going to have sine cubed x divided by 3 plus c. Again, you can check your answer by taking the derivative of this thing. And if you take the derivative, 3 will come down, cancel 3 on the bottom, you get sine squared x times derivative of the inside, which is cosine of x, which is my integrand, plus 0. So it checks. Let's take a step back so you can just kind of see, and I want you to notice how every problem really looks exactly the same. It's set up the same way, so notice. So I want to point this out, so I want you guys to see that these are set up very similar. I have my u, my du, my u, my du, my u, my du. I make my substitution. I make my substitution. I make my substitution. Then I can simplify if I need to, and then I integrate. I integrate, and then I plug back in. Plug back in, plug back in, plug back in. And so I have everything in terms of x in the end. So make sure when you do these problems, you do them exactly the same every time. You write u and du in the same spot, and then you write when you plug back in the same spot. That'll make your life a lot easier on you. Okay, let's take a look at the next type of problem. And let's zoom back in here. So sometimes your du doesn't perfectly match up with your integrand. So let's take a look at an example of that. So here are two more problems. And the first one, you can follow the same format. You say, okay, what's going to be my u? Well, it's going to be that thing on the inside. Now on the bottom one, it's a little bit harder. You have two choices. You can let u be the top or the bottom. If you let it be the top, you won't go anywhere. If you let u equal x, you're going to get back the same thing, because what's the difference between u and x but the shapes of the letters, really. But if you let it be the bottom, you'll get something a little bit simpler. And the idea behind this is if you look at the bottom, what's the derivative of the bottom? The derivative of the bottom is 2x, which is almost the top. And the same thing here. Right? The derivative of x squared minus 1 is 2x, which is almost this x. So let's see how this plays out. So on part A, I have the integral of x squared minus 1 dx. Now when I look at this problem, I know it's not one of my 4 types. It doesn't figure, it's not just a power function. It's this is to the 10th. It's not a power function. It's not an exponential. It's not a logarithmic, like a 1 over x. It's not a trigonometric function. It's not an inverse trigonometric function, and so on. So I know I have to use substitution. So I'm going to let u be the thing on the inside, which is x squared minus 1. And then my du is going to equal 2x dx again. So this is very similar to the problem we did before in the last example, part A. But now when I try to substitute back in, something not bad, but something different's going to happen. So here's my u. There's no issue with that. U is always nice and easy, typically, to plug in. And so there's my u. But now, instead of having x dx, instead of having 2x dx left over, I have just an x dx. But that's okay, because you can get rid of this too. So think about this. Right? If you want to get rid of that 2 because you'd really like to have x dx, how do you move over 2 when you multiply, or you're multiplying by it? You simply do what? You simply divide. So just divide both sides by 2. And so du over 2 is equal to x dx. And then you have it. Right? X dx, this x dx matches up with this x dx, and I just replace it with du over 2. So let's do that. So this is going to equal the integral of, and I have x squared minus 1 to the 10th, so that's u to the 10th. And that x dx, I'm going to cut that out, and I'm going to replace it with du divided by 2. So du divided by 2. And a lot of times, I'm going to run out of space on the right, so I'm going to write underneath it here. A lot of times, you can put this 2 underneath u to the 10th. You could even pull it out if you like. It really doesn't matter. Maybe I'll pull it out. So this is the same thing as 1/2 the integral u to the 10th du. Then it's real obvious. This is a power function, so you add 1 to it. So I have 1/2 u to the 11 divided by 11, then all plus c. And so this is equal to u to the 11 divided by 2 times 11 is 22 plus c. And then plug back in for u, because u is x squared minus 1. And so I have x squared minus 1 to the 11th divided by 22 plus c. Again, you can check this, although it's a little tough because you have to use a chain rule, but the 11 comes down. You get 2 on the bottom, x squared minus 1 to the 10th, times the derivative of the inside, which is a 2x. And so then the 2's on the bottom will cancel, and I'll have x times x squared minus 1 to the 10th plus 0. All right, so this checks. Let's do the next one, part B. So B's a little more tricky. So I have x divided by 1 plus x squared dx. And so again, it's not one of my it's not one of my types. So I have to use u substitution. So I'm going to let u be equal to, and you have two choices. You can let it be the top or the bottom. Now I'm going to let it be the bottom because if you let it be equal to 1 plus x squared, then du is going to be almost equal to this top, this x dx, except instead of x dx, you're going to get 2x dx. All right, now realize you can rewrite this. This is the same thing as 1 divided by 1 plus x squared x dx. And so when I go to make my substitution, u is pretty easy. This is going to be my u. All right, that's my u. And then I'm left with this x dx. Now, I have 2x dx, so I need to get rid of this 2. So the idea is just move over the 2. So if you multiply both sides, if you're multiplying this side by 2, to move it over, you just divide both sides by 2. So you get du divided by 2 is equal to x dx, and you got it. So x dx, which is right here, is just d over 2. So you cut this out and paste that in. They're the same thing. They're equivalent to each other. And so this is going to equal then, what does this equal? This equals the integral of 1 over u, and then x dx is du divided by 2. And be careful, that's a u, not a 4. My u's always look like 4s. And so that's equal to, I'm going to pull out the 1/2, so I have 1/2, the integral of 1 over u du, and that's one of my types. The integral of 1 over anything, d anything, is equal to ln of absolute value of the anything, all plus c. You know, you can put an x there if you want, but that just means anything down there, d anything there, is equal to ln of anything, absolute value of anything, plus c. And so this is going to be 1/2, and then the integral of 1 over u du is equal to ln, absolute value of u, plus c. And so that's equal to 1/2 ln, absolute value of 1 plus x squared, plus c. And you can even drop off the absolute value signs because 1 plus x squared is always what? So think about this. I don't need absolute value signs because if you square something, it's going to be not negative but positive, and if you add 1 to it, it's still going to be positive, so you don't need absolute value signs. They're redundant. So I have ln of 1 plus x squared there, then all plus c. And again, you can check your answer on this. It's a little hard because you have to use a chain rule, but the derivative of 1/2 ln of 1 plus x squared, well, the 1/2 stays. The derivative of ln is 1 over, so 1 over 1 plus x squared times the derivative of the inside, so 2x. The 2's cancel, and I have x over 1 plus x squared, then plus 0 for the c. So it checks. Again, let's take a look back so you can just see how similar these are written. All right, again, so I have my integral here. I have my integral there. Oh, right there. I make my u substitution. So there's my u. There's my u. Below it's my du. Below it's my du. I looked for what I'm substituting in for. I look for what I'm substituting in for, and then I make that substitution. All right, so here's my substitution. Here's my substitution. Then I integrate this out. So I integrate it out, and I get my final answer and make sure I plug back in for x. All right, so they do look quite similar. So try to write it in the same form each time. The integral, the u stuff over here, then go down here, and then just slowly let it work itself out. All right, I'll see you guys tomorrow. Just joking. One more thing. So again, the big idea, right? You take a complex problem. I just want you guys to really understand the idea behind, mathematics and solving problems in general. You take a tough problem, and you do something rather clever and turn it into a simple problem. Right? So you take a tough problem, you do something clever, right? You make this u substitution, and boom, it turns into a simple problem. Right, so you take something that you don't know how to do and turn it into something that you do know how to do. So that's how typically all problems are solved. All right, see you guys in the morning.